to solutions. I'm going to do a final solution problem. It's going to be where I'm taking two solutions and dumping them together and asking you for concentrations of individual ions. We're going to dump in sodium chloride and potassium chloride together. I'm going to ask you for what's the concentration of sodium ions, potassium ions, chloride ions. Okay, so let's review the so when you put sodium chloride in water, aqueous, we've got individual sodium and chloride ions. And these are aqueous now. Now, with the potassium chloride in water, so when we put those together, we've got potassium ions in there, sodium ions in there, and chloride ions in there. Now, the chloride ions are coming from two sources, coming from the sodium chloride and the potassium chloride. So we need to calculate the moles, and also it's a 1-to-1 relationship, okay? So the coefficients are 1, 1, 1, 1, 1, 1. So if we know the concentration of sodium chloride, we also know the concentration of sodium and chloride. This is 1-to-1. We know the concentration of potassium chloride after we mix it now. We know the concentration of potassium ions and chloride ions. Okay, so does that make sense? Now this is about, you're going to have two take-home problems for test 3. You're going to have one on solutions and one on acids and bases. Okay, so let's do this problem now. Okay, remember now concentration is moles per liter. So we need to get the moles in volume. Volume is going to be in liters. So the moles, okay, let's do okay, so the moles of sodium chloride are concentration times volume. So we've got concentration of the sodium chloride is 2.34. Is 123. Potassium chloride, you've got and the volume is 212. Okay, so to find moles, we need to multiply volume times concentration. That'll give us moles. So that's going to be now I got that. Let's see, let's put moles over here. Let's make this moles per liter. Okay, and then 321 times 2.12. Now I did turn up, I did click on record, right? Yeah, okay, okay, so the total volume is gonna be 123 and 212. Now, we're not interested in the moles of sodium chloride. We're interested in the moles of sodium and the moles of chloride. Because the question asks you, what are the mixing the two solutions together? We want to find out all those amounts. Okay, so if we know the concentration of, let's get some room here. If we know the concentration of sodium chloride, we also know the concentration of sodium and chloride. We also know the moles of each. So let's look at potassium, sodium, and chloride. Okay, the potassium are going to be 681. It's a 1-to-1 correspondence between the KCl and the K based on our equation up here after we balanced it. Okay, the number of moles of sodium is going to be 288. And chloride is going to be the same. Okay, the chloride, we have two sources again of the chloride. We've got it from the sodium chloride and the potassium chloride. So let's start adding these up. Okay, so we know the total volume, 335. So the concentration for potassium is going to be moles per liter. So we have, it's going to be 681 over 335 liters. Or capital N. That's for potassium. What about for sodium? We do the same calculation for sodium. And sodium is going to be 288. Right now, chloride, again, has two sources. We have to add those moles of chloride together before we do the calculation. So we've got 288 and 681. Okay, so let's look at these numbers now. We've got potassium concentration is 203. Chloride is 289. Now we want the chloride to be more because we have two sources of the chloride. Sodium is going to be a lot lower. A lot lower. Okay. So this is about as tricky as the problems are going to get. You're going to get a take-home problem similar to this, yeah.
Or 0.8
Instead of 288.
for NA, I got 0.8 59. 8 for 5.
This here,
Yeah, for A plus.
you did not get 897. Is that what you're saying? I mean, 597.
No, I got 8.
That. Good. Thank you. I prove once again I'm human. Okay, walking over here, going uphill with the heat. My stupid packs are so heavy. I've got to dump them out tonight. See what's in there. I've got a bunch of pennies in there. I'm developing a pennies lab and got a bunch of pennies in there, and I'm just hauling them around. You know? Okay, so any questions about this guy? This will be similar to your take-home problem. You get one like this, and then one like with acids and bases. And we haven't talked about doing much of that yet. Okay, so any questions about this? Okay, so let's now talk about acids and bases. I'll start a new one. Notice I put acids, bases, and water. You're gonna see why I put water down there a little while. Okay, so let's start off with some definitions here. I've already mentioned acid a couple times, but let's do it again here. So They are chemical that dissociate. When I say dissociate, that means it's separated from the original compound. There are three types of acids. Let's That's you. Okay. Strong acids, everything comes apart. So if we look at something like hydrochloric acid, 100% comes off. There is no HCl left. It's only H ions, Cl ions. No HCl as a molecule is left. That's what a strong acid is. A weak acid is only part of it comes over, like acetic acid. So in the case of a weak acid, there is a combination of what you start with and what you disassociate it to. Where with 100%, what you start with is no longer there at all. Weak, and most of the acids in the world are weak acids. There are millions of them. I mentioned yesterday we looked at an acid, fatty acid found in meat. 18 carbons long. And it disassociates a little bit, not very much. Still an acid though, because an H plus comes off. Okay, and then a non-acid is just because there are H's there, that doesn't mean they come off. If they don't come off, they're not an acid. Example of that could be ethanol, drinking alcohol. Now, one H comes off. And the reason for that is the C2H5O is very, very unstable. So it doesn't happen. Okay. We've got strong acids, weak acids, and non-acids. Now, we're going to do a lot of stuff with strong acids in here. Because doing calculations of weak acids is extremely more complicated than with strong acids. You have to use a quadratic formula and all kinds of stuff that are ugly. Although there are websites where you just put your quadratic equation in and it gives you everything. So, okay, does that make sense? Strong, weak, no, non-acids. A lot of times they don't talk about non-acids, but it needs to be looked at because there are H's there and the H's potentially can come off. And again, what the difference between a strong acid and a weak acid is how stable is the one coming off versus what you start with. If it's more stable, it happens. If it's only a little more stable, part of it happens. And if it's not stable at all, it won't happen at all. Again, it's strictly a stability reason. Now so what happens after the acid dissociates? There are two parts. This part here is the part that makes it acidic. This part has a funny name. It's called conjugate base, but let me respell that. That's a J. And that's a G. So the conjugate base is what's left over after the H comes off. So acids are kind of made up of two parts. You have an H and a conjugate base together. When they reform, they make the original acid back. Okay, so that's what an acid is. And in our class and the class you're going to be going into, it's in water. It doesn't have to be in water, it can be in other things. Like in biochem, sometimes it's not in water. And you have to deal with different polarities. And for example, that's called a triglyceride, and it's very nonpolar. But when it splits apart, it becomes very polar because the acid part comes off and acts like an acid. What happens is our body needs to move around in the blood. Our blood is very polar, fat is very nonpolar. So what it does, it breaks it up, makes it polar, throws it into the blood, ships it around on a proteins. They're called HDL, LDLs, ships around on a protein, comes back to where it's needed, and then the triglyceride reforms. It's kind of clever way our body works. So, okay, so that's acids. Now, the opposite of an acid is a base. Going to So a base is a chemical that dissociates an OH minus instead of an H plus. Okay, so it's very similar with bases to acids. Our bodies, the world has tons of bases. Sometimes they're referred to as alkaline chemicals, which is kind of the older term. In fact, it's a very old term back to the alchemy days. And you'll see a lot around food-related things. Foods frequently, nutritionally, they always talk about alkaline stuff. They rarely talk about bases or basic. It's always alkaline this, alkaline that. Agriculturally, same thing, mostly alkaline related stuff. Alkaline soil, fertilizer, alkaline everything. Yeah.
Just looking at this and noticing that OH minus plus H plus is just water. So is that why water is perfectly in the middle of the pH scale?
Yes, this is a perfect segue. It's what I'm going to talk about in a minute. Perfect. You will see that before your very eyes. So again, alkaline though is a very frequently used term in terms of bases. In the chemical world, they never say alkaline, they always say base. Biochemists, or depends on whether they're on lean towards the biological side or the chemical side, whether they use the term or not. Okay. So you have strong bases, weak bases, and non-bases. Same argument as with acids. A strong base, like sodium hydroxide lye or potassium hydroxide lye, 100% of the OH comes off. With a weak base, like ammonium hydroxide, is a weak base, only part of the OH comes off. And then the ethanol has an OH on it and none of it comes off. So it's a non-base. Okay, this little aside I want to say about ammonium hydroxide. When you buy ammonia for a cleaning agent, what you're doing is you're buying not NH3 ammonia, which is a gas, you're buying ammonium hydroxide. So when you put ammonia and water together, you form ammonium hydroxide. I have found that putting about this much in a spray bottle with this much water, it's great at killing bugs. And it's extremely cheap. $3 for a jug of Parsons ammonia. You dilute it down in a spray bottle and it kills cockroaches, spiders, flies really well. And if you like to swash them, when you spray them, they'll fall to the ground and they're very weak after that. So very easy to kill if you're into that. But you just keep spraying it and they die. So it's very cheap. I was showing my neighbor that. And he's complaining about how expensive the pesticide is, and he doesn't like my dogs coming in his place because he sprays. I said, and the cool thing about my invention is it's really safe. How do you make it? You make it with ammonia gas at the factory, and you buy it in the bottle. So the next morning, the residue left over is the ammonia escapes again because it's a gas and leaves the result, which is water. So there's no harmful residue whatsoever. Yeah.
You said that.
Huh?
You use it in garden.
Oh, absolutely. Now, when you spray it on a plant leaf, though, plants don't like it as much as bugs. The leaf, spray it on the ground, but for like for aphids and stuff. I don't have a garden. I live in an apartment.
I love it. Not a problem. I applied it. Nothing. I can try that.
You could try it. Why don't you take and really dilute it a lot and spray it? And see if the strawberries are okay afterwards. What do you have to lose? Try it on one plant. Make sure it's got strawberries on it, though, to see how the strawberries are affected by it too. And let me know. I'm real interested. This stuff is so cheap, though. 20 cents. All it takes to make this stuff. With the cost of everything these days, you can pay like $6 and $9 for a bug spray, versus 20 cents. And this is a lot safer. A lot safer. Okay. Now, his question regarding water. Let's look at, let me use some examples here too. Strong base, sodium hydroxide, lye. Potassium hydroxide. Let me tell you how the pioneers used to make soap. You've all heard of lye soap, right? That's called ivory soap. This is what you make it. You take fat and throw it in with lye and boil it. What's left over is soap. It's called saponification. It's a process where an alkaline environment, esters, which is a fat, actually comes apart and becomes soap. So the pioneers, when they were coming across, they always had a pig with them. And whenever they slaughtered the pig, they'd keep the fat and they would use the fat to make soap. Now, to make soap, again, you use lye plus fat, boil it. They got the lye from ashes from their campfires. So if you take ashes from your campfire, put it in water, let it steep for a while in water, you'll end up with lye water. And that's what they boil the fat in. It's very economical. And when you do that, there's two kinds of lye. Potassium and sodium hydroxide. Both of them work the same, but you don't end up with the same kind of soap. One is going to be a liquidy soap, the other is a harder soap. So it depends on how you want to do it. Now, I don't know if they make soap here, but in my class at Sac City, we make soap in the organic class. And then the lab before that, we use steam distillation and pull out the orange essential oil. And we put that in our soap. So it smells nice. It smells like citrusy. Really kind of cool. Okay. Weak bases. Ammonium hydroxide. Ferguson's bug spray. And then if we look at so strong, weak, non-acid or non-base. Okay. Let's now look at the chemical that has both an H and an OH in it, and it disassociates. It's called water. Water is a mild acid and a mild base. Equally as strong. So what happens with water, notice instead of writing water like this, I wrote it like H-OH. So it looks more like an acid and a base. Okay, so what happens is that's what happens. And it's very, very, very small. It's like 0.2%, very, very minor, but it's still an acid and a base. Now, these are all in water. So we can talk about concentrations of these various parts. For example, the concentration of hydrogen ions, unless I put square brackets, that's a shorthand way of writing moles per liter. Square brackets. So the concentration of hydrogen ion in water is 10 to the minus 7 molar. Not very strong. And since this is a balanced equation, the hydrogen ion and the hydroxyl ion, HO minus, that ratio is 1:1. So whatever H is, OH is the same because of our balanced equation. Now, so that's why they say water is neutral, because the amount of acid equals the amount of base. So together you get water. Now our last two labs involve this reaction. Now, frequently, and you've heard of this concept as well, to describe the concentration of H ion in water, they usually don't use concentration numbers, they use something called pH. And for hydrogen ion concentrations, they use pOH. Okay, so what's pH? Who's not heard of pH? Anyone not heard of pH? Okay, low pH is acidic, high pH is alkaline or basic. And the crossover number is 7. 7. Notice it's a negative 7. So the definition of pH negative log of the hydrogen ion concentration. Now, when I teach algebra, back when I was teaching high school, I used to tell my students, they go, oh, a logarithm, that's kind of a fancy name. It's not fancy at all. It's just the same thing as an exponent. So the logarithm of 10 to the minus 7th is minus 7. And logarithms have bases to them. So the common logarithm is base 10. Here we have 10 to the minus 7th. So the negative log of 10 to the minus 7th is plain 7. Now, interestingly, the pOH is the negative logarithm of the OH concentration. So the pOH is 7 also. Now, if you have the pH, you can derive the pOH through the number 14. These together add up to 14. So 14 is equal to pH plus pOH. So if the pH is 2, the pOH is 12. On your calculator. If you don't have a calculator that has a log function on it, you can borrow one. Okay, so do one, it's very simple. Let's say we want to do the log of 10 to the minus 7. I'm going to put 10 caret, I'm going to use y to the x. Change sign, 7. Okay. I'm going to take the logarithm of that. On your calculator, you're going to go change sign, log 10 caret. If your calculator doesn't have a caret, use x, should be a y to the x. Change sign, 7, enter. And you'll get answer 7. Yeah.
If I change sign or if I hit log for comes up there.
Okay, it depends on your calculator. Sometimes you have to hit the log key first, then the number. In other calculators, you put the number down, then hit the log sign. So the alternate way then be to put caret, change sign, 7, log, enter. It depends on your calculator. Like mine, I have to put the number first, then I hit the log key. You still get an error?
Yeah. It-
Anyone else having trouble with getting 7? Line 7. Okay, so here we go. Start with me.
Maybe that too.
When you do the long, no. So. Seventy.
The long. Oh.
Okay, everyone okay with this pH stuff? Okay, so if I said. We actually have a clock that works now, how about that?
Yeah.
So from now on, I'll just ignore you and you'll figure it out.
Yeah.
What did you do differently?
So 10, Y, change sign, 7, log. And then you hit.
Huh, all right, well, keep that in. Okay, so if I asked you. If we have a pH. Of 3. What is the hydrogen ion concentration? Hydrogen ion concentration be? 10 to the negative 3. Now, in math class, sometimes people say there's no such thing as negative pH. Wrong. Take the negative log of 4. What do you get? How much?
-6.
Negative 3.6. 0.3. Is it 0.3?
0.62.
Okay, so the negative 0.6. Negative. Concentrations can easily be 4. When we buy acid from the acid store, Jimi Hendrix, right? No, acid store. It's like 18 molar. What's the negative log of that? .8. Definitely, pH can be negative. It can also be very high as well. Remember, when pH above 7, it becomes alkaline or basic. pH below 7, it's acidic. pH of 7, it is neutral. It's neither acid nor base. Interestingly, Flint, Michigan. Who remembers what happened up in Flint, Michigan with their water? Bad. What is it?
Lead, right?
Lead in the water. One of the problems with how old your community is, sometimes they use lead pipes still. If you live in a house older than 1977, there's a good chance you have something called a lead gooseneck, where the street pipe and your house pipe meet. And they use something called a lead gooseneck, because you can adjust the angle at which the two pipes come together. Now, if your water is acidic, guess what? It leaches out the lead to form Lb or Pb plus 2. Bad, bad, bad for you. Has to do with it. It messes up your enzymes in your body. It messes up the amino acid called cysteine. Screws it all up. And if it happens to be an enzyme, well, an enzyme doesn't work anymore. So, city water, potable water, always checks their pH. They always want it above 7. They want it slightly alkaline, like about 7.2, 7.3. Not acidic at all. Now, I used to teach at Tacoma Community College. I checked pH of the tap water, 6.8. Community Chemistry Department, Tacoma Community College, acidic water. We use deionized water, of course, all the time, but still. And old communities still have that old, like my friend, he lives in a house that was built in the 50s. When he had his pipes replaced because they had roots in them and everything, they found a lead gooseneck. And so I told him how bad it was, so he immediately fixed it, but they're surrounded. And the old communities, the old poor communities particularly, that have not been gentrified yet. Who knows what gentrify means? That means they tear everything down and rebuild with fancy apartments. Gentrification, bad, bad. LA, big time gentrification. I went to a conference one at this really nice Hilton Hotel down there. Gentrified. Hotel was really shiny and new and everything. And we had a presentation to do 2 blocks away. And the guards out said, "Sir, you're not walking that." I said, 2 blocks, it's nothing. He said, "It's dangerous. Take a cab." Because that was the edge of the gentrification in that region. Bad stuff. Anyway, those old areas are really prone to have lead pipes. And children are particularly susceptible to heavy metals in their diet. Really bad. There was a mercury leak in Japan back in the 60s. And until they discovered what was causing all the teratogenation of the newborn, they discovered it was mercury. A plant was dumping mercury into the sea. And then fish would eat the mercury, however, and then the people would eat the fish with the mercury in it. Anyways, so. Okay, so that's pH. On Canvas files, I, of course, have practice for. So if we go to files, acids and bases. Took them out. Anyway, you'll find some practice pH problems. Okay, so that's what I wanted to cover today, an introduction to acids and bases. And we're going to start lab early, really early. So are there any questions about acids, bases, or pHs? Yeah.
Why is the molarity of the H plus so low? Like previous problems, the molarity is never like 10 to the -7. Then suddenly it's like H plus and 10 to the -7.
Well, that's only with regular water. And when you put anything else in it, it changes. You throw a weak acid in the water, it's no longer 10 to the -7. There's 10 to the -7 from the water, plus whatever comes from the acid you put in the water. And you have to add those together.
Yeah.
And frequently the 10 to the 7th is insignificant because it's, remember in it's too low to count. So they ignore the 10 to the -7, but it's there. So,
Is that why the water's like if it's too low to count, that's why water is like the base of
well, it's not too low to count. And someone
it's difficult.
Oh, yeah, pH meter, it reads in pH. Yeah. So it's not.
Oh, yeah.
If it was, but when you're doing calculations like, okay, we have water, then it's -7, and we throw in a little bit of hydrochloric acid. Well, the pH is going to drop tremendously
Yeah.
because of the hydrochloric acid.
Mhm.
So when you look at how tremendous that drop is compared to the 10 to the -7, the 10 to the -7 is basically, we usually ignore it. And usually it comes out in sig figs anyway, it goes away. It's
Yeah.
way at the end.
Yeah. Okay, that makes sense. Thank you.
Better?
Yeah. Any basis? Yeah, on basis. Okay, negative.
Because not 100%.
How does that, so is there still a candidate within this board?
And they charge us. One lot, plus in line.
Would be based, or these are the targets.
What's it is, how much do you got? All the things now, is from the bond. Or is it gonna be under it? With less than a minute in it, in the reasons.
We don't have it.
Well, depends on the. There's normally, you're a force strong base, but most towns. Passing and sorting it out. Everything else is widgets. Or there's a bunch of them us, and you have to look it up. There's no way to say what it is.
For non-faithful. I think there's not.
Because not, none of it always comes up. 0%.
Well, it does not happen all the time.
Right.
Okay. It's just hypothetical.
But this, put 100%. No. It's 0% for this item. So this doesn't happen. Well, yeah.
Oh, yeah.
Fat book. Everything comes from this one. You look at this. Hey.
I predict we're.
If you log, like the people that you involve. Let's go pay, obey.
Oh, it's paper.
It's a ratio to reality. If that cost. If the brain is small. Then.
Oh, yeah.
You look at.
Yeah.
I'll tell you. Now. Well,
Walls of it for the.
Yep.
Yeah. Well, this one.
Same reason. Same reason. Now, is.
Yeah. I got it right here. For a week, acid. Yeah, that's just. The work list. One, but yeah.
Yeah.
So for this, you can't tell.
Yeah. Like an organic.
It's super possible. I knew it was possible. He's a coach. You don't
That increased stability. Shared the universe does not like isolated time. Somehow place it and share it among your atom, you never running parts of the molecule. That's part of this is they right like that, really top. Right like this. Don't. Organic chemistry.
Maybe that's a question.
The higher it is, the more reactive.
That's all my two days. It's not for. It's a lot. I'll go back for this question.
Using this, I will get set.
That's. It's even there, it would be that because it was.
Yeah.
Okay. But second, you show me the box, yes. We can put it.
Okay, let's do this. Let's look at the log of 5. Okay, but remember I said a certain. Yeah. So we're gonna do log 5. So hit the 180.
Okay. Thank you.
It's negative.
Maybe say.
Remember what's told to us. Yeah.
Let me see what I put.
I want this.
I was doing by his. I didn't do it. I was, he did it. That's my bad.
But that's correct, right? Okay, good, cool. Thank you.
So pH is always the negative log. Or just do the log and in your mind you go just negate it. Yeah. That's the way I.
I have one more thing to ask.
Huh?
I have one more thing to ask. But for this, yeah, I would listen to the single this book.
Okay, we look at metal K and N on the reaction series, which is K above N. Okay, and that reaction will go.
That would be a plus an engine.
And now, K to support.
Where would the extra K come from?
And make it balance it.
Just for that. Me or them? Can you introduce? Extra K, bond. Get it done.
Only.
So. So this reaction can go, and the K is going to become ionic. Right now, it's trying to do it. Now, it's ionic. So you. Two Ks.
What?
Well, we have to go on balance.
Spanish.
That's it. Alpha time. First, we have to determine when the reaction is going to go. Then we. Then the cation comes in balance.
So then there happens to be two K.
Better?
No, we're talking about it this morning. I don't know. He didn't do it, and he's still not right. Well, yeah, you have black.
I'm doing it.
I think.
I'll do it. I'll do that. Wait for it.